Okay, you're going to be here for 75 minutes sitting down, so before we begin, stand up. Come on. And sit down again. You have just burnt 0.75 kilocalories, and I have just helped you reduce the chance of getting numerous diseases. Thank you. Before I introduce our speakers, I just wanted to share with you, to set the stage, a little story about a patient of ours who in around December 2011 came to us in our center with a question. She'd been troubled for some time for not being able to get pregnant. And so we're not fertility specialists, but we know a lot of people that are, and so we sent her off to a fertility specialist who sent her off for some MRI scans, and she came back with the answer that the reason she couldn't get pregnant was because she had, from one report, tuberculosis of the womb, which hadn't been seen in somebody like her for maybe 100 years, or, as the other radiologist reported, a completely normal uterus. And it got us thinking, like, how is that possible? How could you have the same scan and two such vastly different reports? Why couldn't we use artificial intelligence, deep learning, things that are now just available in the cloud, to analyze all the scans of people like her and give her a definitive answer, remove this extraordinary variety of different diagnoses that we get from the same patient? 4 years later, and we have numerous startups from all over the world working on this very problem, reducing the variability in diagnosis and helping radiologists make better decisions. So she was just about to start on IVF, in vitro fertilization, and her fertility specialist said, look, I'm going to get in trouble for doing this, but I've just got this funny feeling that before we do, we just need to do an operation to have a look inside and see what's going on, because I really, really don't know why, but I just need to know. She came back from that procedure, and she said, look, I've got some news about why I can't get pregnant. And we asked, well, what was it? And she said, the reason I can't get pregnant, the reason they say I'll never be able to have a child or a family, is because I have cancer throughout the entirety of my womb, which was not picked up on the scan. How is it possible that that intuition that that particular clinician had to do that operation, for which he got in trouble for spending unnecessary money, why did we not capture the reasons why that decision was made, so that we could help other people like this person know what the actual reality was? The surgeons said on Christmas Eve, we need to operate. And she said, look, that means I'm never going to have a family. Is there anything we can do? And so we got some second opinions for her. We sent her to some friends of ours, not clinicians, but mathematicians, who helped her calculate the probability of whether going through a round of egg stimulation and egg harvesting, how that would potentially lead to her increasing the cancer to spread. And they calculated that one round of in vitro fertilization would not be a significant risk, despite everything that her surgeons were telling her. So, against her surgeon's wishes, she picked up a piece of advanced technology, her phone, found out about a fertility clinic open on New Year's Eve, and she started a round of egg harvesting. It was a blind cycle, so instead of getting maybe 20 eggs, she only got 6, but she put them on ice. Then she had her operation, and they came back with worse news. The cancer was not only in her womb, but it was also in her ovaries. It was a stage 3B cancer. Prognosis, 2 years to live. Only possible hope, an amazingly radical operation to remove absolutely everything surrounding those tissues, which might give her some extra chance to live at a great detriment to her quality of life. Again, she asked, is there anything else we can do? So we picked up the phone again. And what did we do? We sent off the tissue samples to be gene sequenced, something utterly impossible only a few years ago at a reasonable price. What was discovered was astonishing. The two tissues, the ovarian tissue and the womb tissue, had completely genetically different cancers. It was not a stage 3 cancer at all. It was 2 stage 1 primaries. By removing them, she'd been cured. A completely different outcome using exponentially advancing technology, a phone in your pocket, genomic sequencing, and just the wherewithal to ask questions and not just accept what the profession is telling you. In around December of 2013, this happened. She found a surrogate mother who very kindly carried the one egg that survived the unfreezing process. And on May the 1st, 2014, this happened. Now, I know May the 1st, 2014 pretty well because I was on stage in London at Wired Health when she told me, she sent a text message to me about the news, and this was the message. I've been trying to call you. Where are you? I'm giving a talk. Anything serious? Your daughter is about to be born. I have an admission to you. She's not my patient, she's my wife, and Sienna is my daughter. What I just wanted to do is to share this story with you because the 4 speakers you're going to hear today are pioneers in medical technology. They don't accept the status quo. They are breaking new ground. And with that curiosity and that passion to advance medicine, my belief is that you can not only change people's lives, potentially save people's lives, but I argue even create new ones. Thank you. So we have 4 brilliant people who I'm going to invite onto the stage now, 3 of whom have come all the way from California. Bing Wang, who is the founder and CEO of Refuge Biotechnology, Kareem Galil from Mendel AI, Harry Gandhi from Medela, and my good friend Mark Koska from Apogee. Please, a big round of applause for these brilliant pioneers. I get to sit on the high stool. So, without further ado, our first speaker, Bing Wang, formerly an investment banker from China who has pivoted, shall we say, into some bioengineering endeavors that are really going to change the way that we treat medicine. Bing, over to you.
Thank you. And thank you for this opportunity. I really want to thank Pioneers Festival for giving this opportunity for Refuge to really introduce ourselves to the world. As of 2 days ago, if you Google us, you won't find anything. Again, my name is Bing Wang. I'm the CEO and co-founder of Refuge Biotechnologies. So at Refuge, we want to focus on the fact that every cell in your body Depending on your body weight, you may have 5 or 10 or 15 trillion cells in your body. Every one of these cells have an incredible ability to compute, an incredible ability to sense. And what we want to do is take advantage of the existing innate capabilities of your cell to make these things a lot more powerful, make them like computers. Think of them as what we're trying to do is little ambulances in your body circulating, looking for cancer cells to destroy or infections to eradicate. But before I go on, let's talk a little bit about the why. And I think a lot of you are familiar with the statistics. Every year, about 14 million people in the world get cancer, and it'll kill about 8 million people. And as you can probably guess, the distribution of survival is very different in different places. Where I'm from, United States, about 1.7 million people a year get cancer, contributing to 600,000 deaths. So the statistics, while horrible, is better than many parts of the world. And the statistics, while horrible, is actually, has been improving the past few decades. In the 1930s, if you were to get cancer, your chances of surviving 5 years is about 1 in 4. So in fact, out of every 4 people, cancer will kill 3 people. By the 1990s, half the people who get cancer in the United States will survive over 5 years. And the most recent data, if you get cancer in the United States, chances are 2/3 of the time you will survive. Okay. Again, this is statistics for the United States. And this is driven by a lot of innovation. This is driven by better pre-op care, better surgery, better targeted medicine, better radiation. It's just a lot of overall improvements in technology and medicine that contributed to this. And one of the more recent technology that contribute to the increase in survival rate is cancer immunotherapy. And I'm sure you've heard of this term many, many times in the past few years. And cancer immunotherapy, in a nutshell, is simply using the idea that your immune system has the ability to target certain cells that just doesn't belong there, and finding a way to either boost its capabilities or find a way to help it to not let cancer cells trick them to kill the cancer cells. So for those of you, and given this is a tech-focused audience, for those of you not familiar with cancer immunotherapy, think of it like this. Think of your immune cells like walkie-talkie. And if you're still in college, you've probably never seen a walkie-talkie before, but it's basically 2 communication devices that talk to each other. Okay? So your immune cells are programmed to target another type of cells. And one of the more prominent ways of doing cancer immunotherapy is called CAR-T, chimeric antigen receptors for T cells. And all it is simply changing the antenna on one of these walkie-talkies so that it can talk to a cancer walkie-talkie. That is state-of-the-art in cancer immunotherapy right now. Okay. Except we realize that your cells are not so much like walkie-talkies. It's more like one of these things. Okay? One of these things. This is the latest and greatest smartphone. Well, maybe not the latest, 1 year old. This smartphone has a lot of capabilities. It has an antenna that can communicate with other cell phones. It can communicate with Wi-Fi and Bluetooth. Your cell has a type of receptor on its surface called GPCR. It can help you see, it can help you taste, it can help you smell. This phone also has a touchscreen that allows you to control the program in it. Your cell also has a cell surface receptor called the integrin receptor that allows it to recognize if it's in contact with another surrounding, like an extracellular matrix. And on some of the latest model, you actually also have a fingerprint reader on your phone. Okay? This prevents other people who's not you or your wife or anybody to access your phone. Your cell, especially your immune cells, have a type of receptors called immune receptors that can recognize differences among millions and millions of different proteins. So one more thing. Your cell phone also has, or at least the latest smartphone, an operating system that consists of ones and zeros. Okay? And this is very similar to the cells in your body, which has an operating system consists of also digital information, A, G, C, T, and most of you know as your DNA. This is actually a very robust operating system, and it's got 3 billion base pairs. And another thing that's been happening in the recent years, past 4 to 5 years, is science has been developing tools that allows us to hack this biological operating system. Yesterday, Dr. Rachel Horowitz from Caribou talked about technology called CRISPR. And for the purpose of this talk, all you need to think about CRISPR is that it is a genetic GPS connected to a pair of DNA scissors. That's all it is. It's a pair of scissors that can cut DNA very, very accurately. Okay? And if we were to somehow replace the pair of scissors with an on-off switch, we have what is called a CRISPR interference. So think of CRISPR interference as simply, again, a genetic GPS connected to an on-off switch. And we can deliver this to any gene in your nucleus to turn on and off programs in your cellular operating system. So, quick summary. I summarized a few graduate biology class worth of biology in the last 5 minutes, but I do want to kind of just re-summarize everything that I just said. The human cells has a very robust operating system, and it has a lot of very powerful sensors on the surface. It has sensors that can detect light, smell, contact, and different proteins. And scientists have developed tools to help you read and write, as well as to turn on and off genes in your body. So great. We can start making nano robots in your body and make you turn into X-Men now, right? Not quite. There's still one missing piece. How do we actually get the operating system and the sensors talk to each other? You see, the idea that human cells have a robust operating system and sensors, that's a very descriptive notion of the cell. Okay? If we want to start to engineer it, we need to do a lot better. We need to find a way to connect these sensors to the programs that actually run them. See, in your cell phone, how does your cell phone actually control the antennas and the touchscreen and the fingerprint reader? With electronic circuits. And these are actually pretty easy to design. 12 years ago, before doing this, and 2 careers ago, I was an electrical engineering professor. I used to teach classes on electronic circuits. I can tell you, this is much, much easier, much, much more simple than the circuits that runs your cell. This is a circuit diagram for just one type of receptor called GPCR. And what you see here is actually only about 30 to 40% of what's actually going on. Okay. Now, for all the engineers out there, you know for you to design a new system, whether it's a new cell phone, new car, you pretty much need to understand 99.9% of the physics for you to do something useful. But we only understand 30 to 40% what's actually going on, how the cell's wired. So what do? Is there a better way to do this? And frankly, in an engineering class, this level of understanding will only get you a C+. Doesn't give you enough to really actually manipulate the cell. So, can we better connect the sensors to the operating system? About 1.5 years ago, 2 very brilliant scientists figured it out. Professor Stanley Chi and one of the postdocs in his lab at Stanford, Dave Dingle. He figured out that if you were to connect a CRISPR interference protein to a cell sensor, that you can find a way to bypass a lot of the circuits and deliver an on-off switch directly into the nucleus to turn on and off any gene you want. And what this does is, since now you have full control from the sensors to the operating system, how they talk to each other, you can change how a cell interacts with its environment. You can program the cell so that it can only activate a cytotoxic, a cell-killing program when it's in a cancer environment. Or you can change the way the cell behaves when it's around other cells. The cell may do one thing when it's with stem cells, and another thing when it's with nerve cells. Or think of it this way. You can also program a stem cell that differentiates into different types of cells, whether it's bone cell or liver cells or any type of cells, only when you tell it to do so. So, what can we do with this? What are some of the cancer applications that we can do with this? So right now, when people get cancer immunotherapy, the drug goes everywhere. And that could be a problem. It can go where the cancer is, but it also goes into a lot of places in your body where there is no cancer. Imagine we can design a therapy that only turns on when it's at the site of the tumor. Or even better, since we know cancer will spread in a lot of different places before it can be detected, we can actually design a therapy that's on everywhere except in certain high-risk organs, like the lung, the heart, or the brain. And we know from some of the recent data that's been coming out from cancer immunotherapy companies that in larger clinical trials, we have more and more people die from some of these side effects. That is a very particular application. So let's think about the bigger picture. What does this mean for medicine going forward? Right now, state of the art. And what I mean by state of the art, I mean now to the next 5 years. When people think about immunotherapy, they usually start with some kind of an engineered T cell, okay, that will target a particular cancer marker. And then they'll combine it with, say, a checkpoint inhibitor called PD-1. And then they'll have to give them some large molecule antibody called anti-IL-6 to repress some of the side effects. And then they may combine it with another checkpoint inhibitor called CTLA-4. And by the way, these are all, at least PD-1, IL-6, and CTLA-4 are already approved on the market. The engineering T-cell will be approved sometime later this year. And there's a clinical trial to add more checkpoint inhibitors, and there's a clinical trial to add additional antibodies to activate the immune cells. But every one of these therapies will be turned on across the entire body, even when the cancer's not there. This is state of the art, and this will be state of the art for the next half decade. Well, not to mention the horrible side effects. Look, I know a lot of you don't know what these things mean. That's okay. Hopefully your doctors will. If someday you will, hopefully you won't, but your oncologists will know. Okay. But it doesn't take a medical expert to see that you put all these different therapies into this poor patient, that you're gonna have some weird side effects, okay? Because the immune system is very complex and cancer is very complex. And let's think about the cost. Right now, state of the art, T-cell therapy is estimated to be about $200,000 per patient per treatment. And by the way, at this price, most biotech and pharmaceutical companies barely break even. Okay. And then we were to add the other therapies that I talk about, another $500,000. So that's about $700,000 right there. Is there a better way to do this? We believe so. With our technology, since we can control how a cell behaves in the body based on the signal it detects and turn on and off genes based on that information, we believe we can come up with better therapy. So how to think about this? Let's go back to my favorite analogy, my iPhone. And for copyright reasons, I can only show you the App Store on my phone. You can tell I use Verizon and I'm not really good about charging my batteries. But on the iPhone, on your App Store, you can pick, these are the games I want. These are the TV show apps that I want. This is the travel app that I want. Okay, you can pick that and customize your phone. Can we do the same thing with a therapeutic cell? I believe we can. Let's go back to the same patient. And let's say this patient has lung cancer. So what can we do? Well, we can design our system such that based on detecting a cancer marker, say called HER2, the cancer cell will now turn off the gene that programs PD-1, turn off the gene that programs CTLA-4, and boost the activation of certain T-cell stimulators. And this is just one therapy. And the manufacturing process for this is actually very much similar to what has already been done currently for CAR-T. So, what have we done so far? Here is a video, okay? And it'll give me a little time to explain this video. And this video shows actually 6 different videos. Think of the 3 on top as cells that don't have the signal that's required to activate this program. And the 3 on the bottom, we actually provide it with a signaling molecule. So, starting with the 2 videos on the left, this is just pictures of live cells moving around. You really can't tell the difference between the 2, okay? But the 2 videos in the middle actually show something. The 2 videos in the middle, we actually connect a protein that emits red light to the CRISPR interference system. So as you look at time, as time goes from 0 over the next 30, 40 hours, we see in the video on the bottom that the cells initially have a lot of light on the edges. That's where the cell membrane is. And the light starts to go in. That's an indication of the CRISPR interference system getting inside the cell, inside the cytoplasm and the cell nucleus But the most interesting video is the one on the right. Here, we include an artificial gene into this cell that will produce a protein called green fluorescence protein that gives off green light. But in its natural state, this program is turned off. Only when we inject this molecule that touches the sensor of the GPCR sensor, and what that causes is the CRISPR interference going into the nucleus and turning on this program, that's when we see the light, green light gets turned on. Okay. So we've done this using CRISPR interference system. Now, for some of you bioengineer experts, you may say, well, there's a few other ways to do this. Not a lot. Maybe there's 1 or 2 other ways to do this. That is true. But because we're doing this using CRISPR technology, again, green fluorescent protein doesn't really do anything for you. It just makes green light. But if we change the guide RNA, all we have to do is just change the sequence of the 23 base pair guide RNA, we have this. We can actually turn on a relevant therapeutic gene. We can make this cell produce additional levels of IL-2. This is an immune activator. Okay? We have similar data for interferon as well. And currently, while this is done in experimental cells, we are actively working on getting this done in primary T cells. So I talked about a lot of different ideas today. I want to go back to the beginning. In the 1990s, 50% of cancer patients will survive in the United States. On the coin toss, I was one of the lucky ones. So this is a picture of me getting radiation therapy in the winter of 2001. I had 4 surgeries, 2 initially, a surgery for rare type of sarcoma on my scalp. And afterwards, I got 6 weeks of radiation treatment. And I remember this. I was the last year in grad school. And I remember every day for 6 weeks, I went in to get treatment for about 5 minutes, 10 minutes on the table. And afterwards, I get ice cream at Halo Pub in downtown Princeton. So just a quick plug, awesome ice cream, helped me recover from radiation therapy. But this is 16 years ago when I had the radiation treatment. And as you know, a lot of these treatment has side effects. So in 2013, a little bit more than 4 years ago, I was diagnosed with a brain tumor, which was caused by the radiation treatment I got. I was very lucky. It was a benign brain tumor. But suffice to say, that was the 5th surgery I had from all this cancer stuff. Today, 2/3 of the people who get cancer in the United States will survive for more than 5 years. Our goal is that in 20 years, we get 100%. Okay? I want to thank you. We are Refuge Biotechnologies. We officially decell today on this moment on stage. I want to thank Pioneers Festival for giving us this opportunity to do so. We're developing intelligent cells that take advantage of all the computing and sensing capability that is in every one of our cells already. We just found a way to make it work. We have preliminary data that shows we can control genes. We control multiple genes. In fact, when we co-incubate our cells with a lymphoma cell line, we can actually downregulate certain genes based on the coding of our single guide RNA. And we plan to start animal studies towards the later part of this year. And like a lot of you, we are looking for money. Thank you very much. Thank you for your attention.
Okay. Thanks. You got time? Maybe you've got time for some questions. Thanks. A big reveal for Pioneers. Thank you, Bing. We don't have microphones in the audience, but if you've been using Slido, there may be some questions which we may or may not have. They do not look like they're appearing, but I have some questions.
Yes.
So, one of the things that I think is a major point of contention with even current CAR T cell therapy, that's the immunotherapy where we engineer the genes of T cells, is the safety aspect.
Yes.
Now, it seems from what you've revealed today that you can possibly make that safer by turning them on or off in a kind of a volume button kind of way, but regulators are scared.
Yes.
Beyond the biotech, what is your approach to the regulators?
Well, I think we're seeing a very positive trend these days. Just a few days ago, there's a drug approved based on the fact, it's a PD-1 antibody, based on the fact that you have one type of mutation, a mismatch repair genes, that anybody can use it, regardless of location of cancer. And that's a huge milestone in biotech. And it goes to show that, at least, comment on the FDA, they are beginning to move slowly forward to understand some of the latest and greatest technologies. So I think there's always a lag between the science, the clinician, and the regulators. And it's like that everywhere around the world. But I believe that the regulators are catching up.
Great. In the interest of time, I think Bing will be available for a lot more in the way of questions at the end. But I think a big round of applause for opening up this new technology to the world today.
Thank you.
Okay, next up, we have Karim. Karim Galil is from Mendel AI, the founder. Originally from Egypt, practiced medicine for 3 years. He will tell you why he pivoted into trying to transform access and understanding of what will work and what won't for individual people in cancer and other diseases. Please welcome onto the stage, Karim Galil.
Hi, everyone. If you know someone in your family or your friends who has cancer, please raise up your hand. So it seems like everyone has someone that's sitting next to him who knows someone with cancer. And that's why I joined medicine. I lost my uncle for cancer, and I was raised that I should grow up and fight cancer. And I went to med school, and I thought I'm gonna be Superman. I'm gonna save lives. But I'm gonna tell you the story of my last patient. My last patient was 30 years old and a good friend. And we did genomic analysis for his cancer. We basically identified an actionable mutation, something that we can act on and we can basically save his life. But we couldn't identify a good clinical trial that can fit that biomarker in an area close by him. And we lost the patient. Literally a week after that, we got to know that the trial that would fit this biomarker was happening few miles away from where he lives, but no one in the hospital or even the other hospital got to know that this is an option for the patient. This is not a story that happens once, and it's not a story that happens only for me. If you go to MD Anderson, so MD Anderson is the world's best cancer center, and they did a research on 1,000 patients in their own pool of patients. And they identified that 39% of these patients did not access world-class treatments, and I quote, due to the lack of awareness of the physicians. So we're talking about the world's best cancer center. If you go to a community hospital or more of a rural area, this can jump to 95%. The problem in cancer is not only that we don't have enough solutions, but even if we know those solutions, your physician does not stand a big chance for knowing it at the right time. That is not because physicians are stupid. We're trying to do our best. We spend all our time studying and trying to save patients. But if you get to know that every year, medicine publishes around 700,000 papers, and an average human being can read only 200. Dr. Jack was talking about his patient, and they had to take second opinions and call other physicians. And that's how we practice medicine today. To access the world's knowledge, you have to make tons of phone calls. And you have to be lucky to make the phone calls to this guy who knows that paper or that piece of information that fits to your specific patient. Now, hypothetically speaking, if we get a human being to not sleep, eat, go to the restroom, he's just gonna sit down and read the 700,000 pages papers published every year, he now has to go through terabytes of medical records per patient to identify which paper actually fits that specific patient. So it's a humanly impossible job. And it's also a great problem for AI. And this is how we do AI in healthcare right now. We use natural language processing to deal with the unstructured data, but we use physicians and domain experts to create rules that can help the AI identify a proper solution. So this is a rule, one of these rules. If you find the glucose levels to be at level X, please conclude Y. The problem is, medicine is way more sophisticated than that. In medicine, we need millions of these rules. And we need to hire millions of physicians to sit down and kind of imagine all the possible scenarios that may pop up. The result is we have an AI that is cripplingly literal-minded. It is not, it doesn't think like a doctor. It actually just, it's full of boxes, full of rules that doctors ask the AI to think like it, and nothing new comes up. So we find big hospitals now ditching AI solutions because they didn't find any new or added value that the AI system has brought to their hospitals. Our approach is we don't want to box rules into the AI. We actually want to train the AI to come up and build its own rules. We want the AI to surprise us. We want the AI to tell us something that we didn't know without it. This summarizes how we think of our product at Mendel. It's a triangle. We have to generate tons of training data to be basically able or to stand a chance to build an AI system. So we built partnerships with different hospitals, and now we have over 40,000 medical records and over 100 physicians sitting down, curating those medical records and finding all the possible alternatives in research that can fit to every specific patient. This is an enormous and high quality training data that give us a huge advantage on picking which solution we should use. And we were able to use deep learning. We were able to use technologies that is used for translation and is used for sentiment analysis, and we brought this for healthcare. We basically built a domain customized neural network that can grasp all this training data and kind of realize how can you read, but most importantly, think like an oncologist. Then we figured out that if we have the best technology, but nobody's using it, it's useless. So how can you package AI in a way that the physician can interact with it? He doesn't have to log into a different website. The patient knows how to interact with it. That on its own is a big challenge. So I'm gonna demo our product, but before that, this is our biggest competitor that shall be unnamed. It's obviously one of the biggest IT companies. They started the computer industry in a sense. And when you mention AI in healthcare, you always mention this company. And this is how their system is today. It's basically full of different questions that you need to answer, and based on that, clinical trials and treatments are suggested. So the demo. There's no demo.
Is it the wrong slide?
The demo is not appearing. Oh yeah, here we go.
AI is easy, AV is hard.
So this is a PDF. It's basically medical records for one patient. We de-identified the patient. And as you can see, it's 44 pages worth of medical records. What I'm gonna do here is you log into Mendel and we upload the medical records. The system analyzes the medical records and starts identifying all the relevant information there and matches it to a huge database of all the clinical trials that exist and open for recruiting patients at the moment. Then it starts listing the treatments for you based on how good of a match is it. Let's open one of them. So this is one trial that fits that specific patient, but as a physician, I want to know why did the AI think it's a good trial. The AI basically starts comparing the eligibility criteria of the trial versus the medical records of the patient and color codes them. If it's green, it basically means it's a match. If it's blue, it basically means we don't have enough information within the medical records that can tell us whether this is a good match or not. If it's black, it means it's an irrelevant piece of information. And based on that, we calculate a matching score and we start ranking the trials. We do not suggest trials, we rank trials. The ultimate decision is for the physician. So Mendel is not to replace an oncologist. Mendel is to augment the capacity and the knowledge of the oncologist. Think of it as, that's how I think of it. If you are an Iron Man fan, it's like Jarvis. It's something that helps you, that augments you, that gives you wider access to the complete knowledge that we as human beings know right now. We also add videos to help the doctor explain to the patient what kind of treatment that is. We back it with all the publications that back that specific treatment and why is it relevant for that specific patient. We're running out of time, so I'm gonna go back to my presentation. And a few years ago, we knew that cellular phones are inevitable, but we didn't know that there's going to be an iPhone. That's how we imagined cell phones. And these days, we know that AI is inevitable, but we don't yet know what is the iPhone. What is that AI system that is not, if you want to scare a kid, just go to Google Images and put AI, and you're gonna get all pictures like this. We as humans freak out from the AI. We get a lot of our patients writing on our Facebook pages that they do not trust AI. So how can you package the AI? That's the real big question. We did a lot of progress. We have a lot of AI tools, but they're not packaged yet to be humanly friendly. They're not packaged yet to be able to augment a physician or an oncologist without actually interfering with his daily routine. If I want to leave you with one thought, this is a Facebook post that kind of summarizes why we're in business. This lady lost her husband, and few months later, she found about a trial that would have saved another patient with the same exact cancer like her husband, and she was never given the option. The idea about Mendel is not giving you the cure for cancer, but it's giving you the right to access all the options that may save your life. We're not promising to save anybody's life, but what we're promising is, if there is any hope, you deserve to know about it. Anybody with internet access, whether he goes to MD Anderson, whether he goes to a hospital in Egypt, or even a jungle in Africa, deserves to know what is the latest treatment for his specific type of cancer. And we cannot do that without AI. For me, AI right now draws the fine line between life and death. And it's a mission that we need more people to help us working on. Thank you so much.
Awesome stuff. Well done. So I've got some questions. Unfortunately, the Slido thing isn't working. So again, Kareem and everyone will be available afterwards. So you're just going to be left with me and my questions. So the toughest ones.
Okay.
Amazing work. I was fascinated to see how that actually, operates from a workflow perspective, which is really amazing. What are the challenges that you're seeing actually in places that you're, getting your first adopters? What is the reaction from the clinicians themselves? And I'm not talking about the ones that are, the first people to buy smartphones and so on. I mean, the ones that, are basically the whole population that you need to kind of convert.
That's a great question. So the biggest constraint is the input and the output. How can the physician input the data without having to log into our website? And how can he get access to the results without having to go outside? So we find out that doctors spend a lot of time in front of their EMRs, in front of their medical records, and they're inputting data already. So we're integrating our API now with different hospital systems. So in real time, while the doctor is inputting data, we're reading this data and we're suggesting treatments while he's already working on it. So he doesn't have to actually adopt Mendel. Mendel is already existent in the framework of his daily routine in a sense.
So I'm an oncologist. I'm not pretending. I've got a patient and I click the button, which is the big Mendel AI button. And it comes up with a whole bunch of trials that are just down the road at a competing university hospital. How does that work? How do you foresee that conversation evolving when, I'm an academic oncologist, I want you to go on my trial because I fancy some new metabolic therapy, and just down the road, there's something probably better for me, which is, I have to give up my patient. How do you see that working out?
Yeah, so we work with the hospital management, and if a lot of their patients are actually a good match for a trial that does not exist in the hospital, we basically bring the trial to the hospital. So that's a money-generating function to the hospital in a sense. So we work between the hospital and the pharma company. In a sense, we start predicting which sites can actually recruit for a specific trial. In many cases, the trials are not happening in the right site. So we give an incentive to start referring outside the hospital, because in return, if you refer as many, we can actually bring the trial or the sponsor to your hospital. But to your question also, in Memorial Sloan Kettering, we find it funny because there's a lot of trials happening there. And you can find 2 oncologists running 2 different sets of trials, and they don't know what trial is happening in the next door, not in the next hospital. So we would be surprised. A lot of the trials are actually in the same hospital, but nobody in the hospital got to know about that.
That's true. So you made a relatively big claim about IBM Watson. IBM are not terribly happy with me because I stole their chief medical scientist who was head of Watson.
I hope they're not happy with me
they
too.
were not very happy. But how are you going to sort of prove your point?
That's a really good question. So, all of good questions. Okay, so we don't have $500 million or $1 million to market our stuff. We don't have that. But what we do is we have actually a working AI, not an AI. So I would like to announce a challenge. I'm willing to run 1 patient on our system and run the same exact patient on their system or anybody else's system, and let's see how the results compare. So if you guys are up to the challenge, please tweet that. Mendel is ready for a challenge versus IBM Watson on 1 patient that they pick or we pick, whatever, and see how the results would compare. Because otherwise, there's no way I can prove my point.
David versus Goliath.
Thank you.
Well done. So we've gone on a little journey from sort of extreme edge of bioengineering that maybe may take a couple of decades to solve some of these problems, through to the cutting edge, things that are in trial, how to best match ourselves to those things that are not widely available or known. But what if we focused some more attention on preventing disease? Next up, we have Harry Gandhi, who has also come all the way from California, originally from Canada, who's going to talk about some extraordinary technology for biosensing and predicting and helping us avoid disease in the first place. A round of applause, please, for Harry Gandhi.
Thanks. Oh, it's a pleasure to be here. Now, before I get into any technical details, I just want to share a story that really motivated me to do what I do. And it's a story about David. Now, David was an avid biker who loved taking his bike out. One hot summer day, as he was cruising through some of the most beautiful trails, he felt slightly dizzy, and he fainted in the middle of his ride. This is a condition that can happen to any one of 4 million people who suffer from diabetes across the globe. And it's not just this. They suffer from many other recurring conditions such as stroke, seizure, and can lead all the way to organ failure. And by the way, that wasn't just a story. It's a true event that happened to one of our co-founders' parents, and that's what's got us started on this problem. So why is diabetes management so hard? It's because current solutions are discontinuous, they're invasive, and above all, not compliant. That leads to 20% of the patients doing the type of monitoring that they should be doing. Now, to solve this problem, we're building a contact lens that continuously and non-invasively monitors glucose levels and sends that information to your mobile phone so that patients can better manage their health. And by the way, these aren't just renderings. We've got our prototypes made and developed. So how does it work? The contact lens is made up of 3 main parts. First, the sensor itself that's responsible for sensing. Second is what we call the ASIC chip, which sends and processes the information. And the third, which is the antenna, which sends the information out of the smart contact lens to a mobile device. And the way you connect to a mobile device is one of 2 ways. Either you can tap your eye and get a glucose measurement just like that, or you have a small clip on your collar that's continuously taking glucose measurements as your day progresses, warning you about the highs and lows and before anything serious happens. And this wouldn't be possible with the tremendous help that we get from our partners, researchers, and collaborators. ranging anywhere from nanotechnology all the way out to large, large antenna labs that make this technology possible for us. But we don't want to stop there. Turns out your tears are just a diluted version of your blood and have the biomarkers necessary to monitor a variety of diseases. We've created this internal project. We call this the periodic table of biomarkers that allow us to monitor a variety of markers that tie to cardiac health, cancer, and other inflammatory diseases. And that's really where the journey of preventative medicine happens. We suffer from this problem of data collection. So why start with glucose? The simple answer is we're so used to it. We're used to spending money to go towards glucose monitoring. As a matter of fact, we spend close to $20 billion every year on monitoring our glucose. That's not therapeutics, that's just monitoring our glucose levels. Here are some facts that I think most of us know, but the key one here is this is one of the biggest epidemics as it's decided by the World Health Organization and will be the 7th leading cause of death by 2030. But I come back to this. How do we really drive a vision of preventative medicine? And we've been made this promise time and time again, whether it be genomics, whether it be biochemical sensors, we've been promised preventative medicine for the last 3 decades. And why haven't we seen this growth of preventative medicine? And I can boil it down to 3 main factors. We've seen articles like this time and time again where we see promises come out on preventative medicine, and it's limited by the 3 blockers. First, we suffer from a data collection problem. We don't have high quality data about what's happening around us. We might know exactly how many clicks we've done on a mobile app, but we have no idea of what our glucose levels are, what our cardiac markers are, what our ion concentrations are. We might be able to track how much we walk every day or putting our phones beside our bed when we sleep, but we really lack the high quality clinical understanding of our health. The second is the problem of data organization. Taking this data of our health and converting into information, and the type of stuff that the Mendel AI guys have been working on. And the third problem is the problem of health economics between the 3 Ps, the patient, the provider, and the payer. And how each of these 3 groups are incentivized dramatically changes depending on which healthcare system you go to and how patients get treated today. Our job at Medela is to work on the first problem of this journey, specifically the data collection problem, by building the sensors and having high quality data that we need. So a future could look something like this. Not only would you be able to monitor your glucose levels and your fluctuations, but you could also monitor things like cortisol. You can also monitor things like osmolarity. And each of these fluctuations not only are independently valuable for different disease outcomes, but we can also look at data between diseases, how one disease can lead to another disease, and possibly be able to prevent that. This is what I call vertical data organization, because we go deeper into a human being and how him or her takes metabolism, takes their personal health into their own hands. The second is what I called horizontal data organization. So before working on Medela, I used to work in e-health, and one of the projects that my team worked on was mapping different diseases. We took information from about a local area of all emergency clinics and tagged that information, which was static data points. But because we were collecting such a high group of data, we could predict the movement of flu and how the disease progressed across different geographies. Now imagine if everyone had a contact lens that could monitor multiple biomarkers. The resolution of that data for someone like a Center for Disease Control, monitoring in hospitals would be much, much better. And we can not only drive a better system for our patients, but a better system for doctors and clinicians to operate in by driving those economic forces down. But this is still a ways away. What we need to focus on now is the data collection problem, having the right data to the right people at the right time. And the way to do this, like I said, has been tried time and time again, but it comes from the intersection of the following things. It comes from the intersection of seamless monitoring, something that's like air. It's there, it's doing its job, but we don't realize it, and making it so easy to monitor our health, coupled with the high-quality clinical data. These two things in accordance is what will build the future of preventative medicine. And I want to leave you with the following thought. In the time that I started speaking, 10 new people, just within the last couple of minutes, were diagnosed with diabetes, 8 of which were preventable causes. Take those numbers in just for a second, that we could have prevented people from capturing a certain disease, but we weren't able to because they didn't have the right data at the right time. That's why we started Medela Health. We make health monitoring seamless. Thank you.
Thanks, man. Fantastically, you have a few minutes spare, which gives me a bit of a Dragon's Den moment. I've been doing a bit of competitive analysis, and I came up with one competitor. I can't remember its name. Google.
Yeah.
Google's Iris.
Yes.
Could you put some color around how you and Iris are working together, or?
So, yeah, there's actually 7 smart contact lens companies in the world, each different in its own way with different merits. One core belief that we have is in order to make this technology accessible to the wide majority, one thing that needs to come down is cost. Too often do we see technologies, that are making amazing progresses across society, but they're only meant for less than 1% of the entire population. And we focused on that element and kept that metric in mind in developing our technology. And specifically, we've made our sensor technology that not only can it last for 1 day, but it lasts for 1 month, whereas Google's technology lasts for 1 day. This gives us a big edge and brings the cost down from what you could spend tens of thousands on monitoring your glucose levels to less than $2,000 per year per patient. And that's uncorrected for insurance, so we anticipate that to go even further lower. The reason why this is important is because type 2 diabetes patients are already used to spending this type of money. And the only way to get them on a new solution is not only does it have to be seamless, have high quality data, but cost is a big factor. And that's our key focus.
Okay. Well, one more question for you. We've got this stack of collection and organization and of data and then the economics of it. One of the big challenges that I've faced in my projects, as many people have in prevention, is who pays for prevention? Because the results are maybe manifested only 20 or 30 years from the time you start preventing the problem.
That's a very good question. The way, and I can give a talk on this separately, but the way at least it's structured in the US and Canada, the systems are not made with the best interest of the patient in mind, given where just dollars flow. So there's not a perfect answer to how can we bring those economics down without affecting each of those parties. The one thing that I can say is the trends are positive, where insurance companies as well as governments are looking to change these regulations such that it's more catered towards patients. A great example from my hometown in Toronto and Ontario, the government has been passing laws to drive down what's called, instead of a service-based model of care, to an outcomes-based model of care, such that the doctors, the insurers only spend money if a positive health outcome is used, aka allowing for more and more health monitoring to drive health outcomes, as opposed to just doing particular therapies or particular clinician visits and getting money based on that. So we're seeing positive trends. We're not quite there yet, but give it a couple of years and I think we'll be in a very good situation.
Good luck.
Thank
you very much, Harry. Finally, we have someone that's going to bring us, I think, back down to earth in a lot of ways. We've heard about bioengineering. We've heard about software engineering. We've heard about hardware engineering. But what about whole global healthcare system engineering? I have the privilege of introducing our final speaker today. He is a friend of mine. He is an inspiration to me. And when I set out on my path beyond clinical practice to try and impact lives beyond just the people I see in my clinic, to reach global audiences, Mark's name popped up, and ever since I've been truly inspired by his work and his continuing passion to change not only the lives of hundreds or thousands or millions, but in fact billions of people all across the world. He famously invented the self-destructing syringe, which has prevented the spread of HIV and hepatitis in literally hundreds and hundreds of millions of people across the developing world. And he's here to talk about, with me, in a stand-up, fireside discussion about his new work, his new ambitions, and his hopes for global health. Mark Koska. So, Mark, I don't know if you have any slides, but do we abandon this? Do we have any?
Let's throw that away.
Throw it away. Mark, tell us a little bit, first of all, about your journey from the self-destructing syringe and Apiject, which...
Okay. Well, let's start at the beginning. So 33 years ago, this month, I read a newspaper article which predicted, and this was in the AIDS era, the psychotic reaction to HIV, 1983-84 period. And I read a newspaper article that said it was a prediction that one day syringes would be a transmission route for many viruses. This wasn't necessarily through drug abuse, this was through healthcare workers. And I was fascinated by this one prediction. So I spent the next 3 years doing something which I'm very passionate about, which is researching the problem. And I looked at how plastic was refined from oil, how syringes were made, packaged, sterilized, warehoused, distributed, all the way through to their end use. And after 3 years, came up with a decision that if I was going to help in this area, I had to come up with a very simple solution, and that's what I was able to do. And I'll demo it in a second. It took 17 years from first reading that newspaper article to sell the first product to the UNICEF organization, who by then had put in some legislation which said that if we were going to immunize large numbers of people, and it was going to be funded by the Gavi, the Global Alliance for Vaccine and Immunization Organization, that they had to cut out that possibility of reuse. And we were able to jump on board, and a few more years involved there, we were able to supply them. And now we've become actually the biggest supplier of these syringes to UNICEF. So this is what it looks like. It looks exactly like a normal syringe. My innovation, if you like, was to manufacture on a standard manufacturing setup for the same cost and used in the same way. So it looks like a normal syringe. You adjust the dose, etc. You give the injection, but if you try and reuse it, it locks and breaks inside the barrel, so you can only use it once. Thank you. So we've gone on to sell around 7.5 billion of these devices, and because there's a transmission rate, unfortunately, of normally hepatitis is the biggest marker that we see transmitted. We've seen, 1 in 100 might result in a fatal infection. So we're very proud of that intervention and how that's gone. I then took a couple of years off to lobby the World Health Organization because the aforementioned immunization market was very well protected with this mandate, but it didn't apply to the rest of the world, and the rest of the world is 90% or more, what we call the curative market. So hammering on doors, a little bit of troublemaking, and last year we were able to pass only the third ever global mandate in 70 years with the WHO, the first one being polio and the second one hand washing. So by 2020, all syringes have to be of this ilk, have to be safety engineered, including the needle. And then moving on, I was really worried, I was really bothered by the fact that the syringe is only one element, and There's no guarantee that you're going to bond with the process before or the process afterwards. So why would manufacturers want to make a better syringe? There's no incentive profit-wise for sure. And in fact, one of the things that is true is if you use safer syringes, in 5 years' time, you need less because you're not transmitting disease. And in fact, for every dollar spent on safer technology, the world saves $14, as you mentioned to Harry, at some point in the future. There's a 1 to 14 payback, which is phenomenal.
Yeah.
So I was very interested in the whole ecosystem, and a couple of examples here. So we have a glass vial. A glass vial is around 100 years old in technology. We make around 50 billion of these a year, and they're absolutely useless for carrying drugs. I know it's the default, but they have a lot of problems. One, if you drop it, it might break and smash. In fact, 15% of all glass vials break from the point of manufacture to the point of delivery. They actually shed particles into the contents as well, delamination. And they take a long time to make and a lot of energy. They take months to make.
And they're not light.
They're not light and they're bulky, and they can be infected because you have to put the needle into the vial to get out the drug. If a dirty needle goes in, it infects the rest of the content.
It's interesting because we kind of familiarize ourselves with this being kind of a holy object. You know, it's that beautiful crystal clear fluid and that you turn upside down and you put the syringe in and draw it out. But in fact, it maybe isn't as pure as we think.
There's a visionary guy 60 years ago who invented this process. This is called blow, fill, seal, and I'm sure many of you used it for eye drops or washing out your eye if you got a splinter in it. They're in most medical packs. And these are incredible. They were designed 60 years ago. They're made in a few seconds. They're sterile. There's no particles. And it had always been the dream of this company to package parenterals or injectables. And so far, they haven't been able to do it. So I was looking at this, and I decided to make a fitting which goes on top of this. And the way this works is we've designed a little needle cover which fits with the bottle, locks in place, has a valve in here so you can't draw in body fluid, you can't refill it afterwards. And in fact, if I can let the cameraman zoom in, if you just squeeze the blister, you can see that you can deliver an injection. Now, these things are incredibly light. They're very, very small, so we can literally fit 6 or 7 times more on a container for UNICEF, for example, to ship them around the world. We can fly them on drones. In fact, 800 of these with the vaccine weigh 2 kilos. So we can fit them on every single available drone.
How many kilos are 800 of these with the syringes and,
with the syringes,
and the needles?
A couple of Land Rovers.
Wow.
So we're talking about a small drone taking this as a payload, and we've designed them so they concertina together, they fit together in very tight configuration when they're in the packet because they lie together like this. So that's 10 of those units in just there.
Wow.
So using blow, fill, seal and using different length needles, we're also able to open up different opportunities. And this project's really about access. So for example, here, again, very hard, I think, to see, is a very short needle. And this is used, as you will know, for delivering intradermal injections.
Yeah.
And intradermal injections have probably the fastest growing potential for delivering vaccines and drugs. And what's important about it is that they're not scary.
Yeah.
And the beauty of this new system is that it's already approved for self-delivery. So
does everyone know what an intradermal injection is? It's when
very
you
shallow.
Put it underneath the skin. It doesn't go under the dermis. It's just literally the very, very superficial parts of the skin, which in fact enable the immune system to really react strongly. So specifically for vaccines and things, it's a great place to put an injector.
And new research says that insulin is far more effective. Yeah. And you only use 1/5 of the dose. So we're shipping much less around the world. So we've never had a device to deliver intradermally. But the big news in this project is that this is already approved for self-delivery. And that suddenly changes the game to access completely, because instead of relying on a healthcare worker who's the big bottleneck in this whole system in the developing world, and we're not talking about these amazing technologies here, we're talking about the 6 or 6.5 billion people who live below that line and will never see this technology in their lifetime. But imagine being able to deliver full childhood immunizations because they can be delivered by their mum or their dad. Or imagine being able to react to an outbreak of something, an epidemic, in a far more cohesive way, and because we can pack these things in seconds rather than waiting months for the supply line. So it is a game changer, and it's super exciting, and we're on the road.
Do you have a little kind of story behind the inspiration behind this, which is why it's called Jack?
Well,
Apis
apis is Latin for bee, and it's based off a bee sting for obvious reasons, because it's a little bladder with a needle, which is how bees very effectively give us a little reminder every now and again that they're quite valuable. My wife and I keep bees. Well, my wife keeps bees at home, and I help her now and again. And so I was having an argument with someone. I was a bit pissed off, and a bee flew past me, and I kind of asked the bee the question, how would you do it? And the bee answered. So.
What kind of injectable were you on when you... Joke. Well, we've come basically nearly to the end of our session today. I think what you, for me, have done over the years is equally as extraordinary, if not more extraordinary, in some of the bioengineering and AI efforts that we're seeing, because you're doing what is really important, I think, for everyone in medical innovation. It's not just about the new technologies, it's about equity, access, and affordability. And that fundamentally is what we need to drive towards. And my challenge to everyone who is involved in any kind of technology, medical or otherwise, is don't just think about the far future and of excellence. Think about equality, think about equity, think about affordability in everything that you do. And Mark absolutely demonstrates that not only technological engineering, but also whole healthcare system engineering is possible, and it can happen from just one person and a little bee. Thank you very much.
Thanks, man.